The work that I'm going to be talking about today is on the dynamics of RNNs as they perform various text classification tasks. So the motivation for this is that RNNs have recently become very successful in tasks like language modeling or translation, but because they're such high-dimensional nonlinear functions, it's tough to understand what computations exactly they're doing, and thus they're often treated as black boxes. And while we have various tools for interpretability, which largely work at the single neuron level, in this line of work, what we hope to do is leverage the fact that these RNNs are ultimately dynamical systems, and therefore we can use tools from dynamical systems analysis to try and understand what sorts of computations these networks are performing. Now, the work that I'm going to be talking about today builds on some prior work in the past couple of years from folks at Brain, which showed that in the simple task of binary or two-class sentiment classification, the dynamical systems learned by the networks were actually both low-dimensional and interpretable. So this work is sort of building on that work towards understanding things like language modeling or translation. But before we do that, we want to, in this work, understand how RNNs work on n-class text classification, where n in this case is now greater than 2. So in particular, I'm going to be talking about two different types of text classification tasks. One is a categorical task, for example, classifying a news article into, let's say, a sports or business category. The second type of task is an order task, for example, classifying, let's say, the number of stars that a user left along with his or her review of a certain product. So the first thing we find is that just like in the binary sentiment case, the dynamics of the trained RNNs on these tasks are low dimensional. And this is perhaps the most important thing to take away from this talk. So what I mean by this is that even though the hidden state of the RNN is 128 or 256 dimensional, if you look at the set of points an RNN visits while it's performing computation, that set of points is much lower dimensional. And in particular, in the case of categorical n-class classification, that set of points is actually n-1 dimensional. So this fact, along with the fact that the linearized approximation of the RNN works quite well, allows us to get a pretty good handle on what the RNN is actually doing to solve this task. So for example, in the case of three-class categorical classification, for example, classifying a document into world, sports, or business category, in this case, the trajectories are largely two-dimensional. And when we look at them within the top two principal components plane, we find that they fill out a triangle. So essentially, each vertex of the triangle corresponds to one category. So there's a vertex for world, vertex for sports, vertex for business. And every time a network sees a word which indicates evidence of a particular class, it moves its position within this triangle towards the corresponding vertex. So for example, if it sees a word like bankruptcy, it moves towards the vertex of the triangle corresponding to business. And this sort of motion is supported by or enabled by a manifold of stable fixed points. And when we linearize the dynamics of the system around these fixed points, which, as you can see, form a triangle, what we find is that there are two long-lived eigenmodes of the system which live within the fixed point plane. So using these two eigenmodes, the network is integrating evidence or keeping track of evidence for each class as it goes through the document. So this underlying mechanism also explains the n-class categorical classification beyond just three. So for example, in the full four-class AG News dataset, we find now a tetrahedron of fixed points. So the general principle is that in categorical classification, the network uses n-1 dimensions to keep track of relative evidence for each of the n classes. Now, this same principle holds for ordered classification, except in this case, the network doesn't actually need to keep track of the full n-1 dimensions. So in this case, here we have a 5-star classification network for either a Yelp or Amazon review, but because of the ordering, it turns out that the network only needs to keep track of two properties of words, which in this case roughly correspond to valence, that's good or bad, and intensity, which is neutral or intense. And in the paper, we show how we can explain this 2D geometry by using statistics that we compute on the training dataset itself. So the moral here is that we have an integration manifold, but because of correlations between classes, we have one of reduced dimensionality. So in this work, we've learned how RNNs perform various text classification tasks. And in the future, we want to use these tools to try and understand the dynamical systems which underlie more complex RNNs, for example, language models and translation. Thank you very much.